So let's start with this one. We have he's saying, do you want me to do any other paper apart from this? Okay, so this one is that the structure of this molecule is shown, and he's saying complete the equation for the reaction where this acts as a base. So why will it act as a base? Because it's got nitrogen, which has I mean, as you know, nitrogen has lone pairs. So you draw the whole molecule, draw the benzene, and C double bond O, and O, that's an ester link. Then you got 1, 2, 3, and 4. And there's going to be an NH2, and it would become NH3 plus 1. It will accept an H plus 1 ion. The lone pairs are going to attract the H plus 1 ions, and it will act as a base. That's the first one. Then he's saying it's a stronger base or weaker base than ammonia. Give a reason for your choice. So the reason is it's a weaker base. This is ammonia. Ammonia has these lone. Yes.
Which paper is this?
This one is W19 question paper 4.3. Winter 19. I said, now is it a stronger base or a weaker base? So it's going to be a weaker base because when it comes to bases, it all depends on the lone pairs and the charge density of those lone pairs on N. So over here, the lone pairs would mix up with benzene's electron cloud. If they're going to mix up with benzene's electron cloud, the charge density is going to be lesser. So this is what you're going to write, that lone pairs in this molecule. What is the name of the molecule? Lone pairs on N. So lone pairs on N in this molecule, they overlap with benzene's pi electron cloud. And the charge density decreases. So there's going to be lesser attraction for lesser attraction for H plus 1 ions compared to ammonia. Hence, it's going to be a weaker. This one is going to be a weaker base. So is this clear? And remember, if you had an alkyl chain with, just for revision, if you had an alkyl chain with N, then it would have been a stronger base because alkyl chains have an electron donating effect. TK, is this clear? Ethan, Sohail, is this clear? Now, next one is they're showing this molecule and they're saying that it's separately, I think you have to draw them. So what happens when you, this is when diazonium salts are produced, or the unstable diazonium ion. This is something that we did last time. The NH2 becomes N triple bond N plus 1. So everything remains kind of exactly the same. Again, you have benzene with C double bond O and O, followed by a carbon chain, and this side becomes N triple bond N plus 1, diazonium ion. When you react it with bromine, bromines, this is an activated benzene. So that means the electron density is higher at positions number 2 and 6 and 4. So it's an activated benzene. So bromines are going to get attached to, bromines are electrophiles. They're going to get attached to those positions. So this would be NH2. And you'll have bromines getting attached to position number 2. And remember, it's a highly activated benzene, which means you don't need a catalyst as well. When you have phenols and when you have NH2 amines attached to benzene, the lone pairs mixing, it increases the charge density of the benzene, which is why it's very, very active. So bromines are going to get attached to both positions. And then you're heating it with NaOH aqueous and reflux. With NaOH aqueous, this would be basic hydrolysis, alkaline hydrolysis. The ester link will break. So you're going to get two products. One of them would be, NH2 remains exactly the same. The ester link over here will turn into a carboxylic acid, and the O that was followed would turn into an alcohol and followed by a carbon chain. And in alkaline hydrolysis, what you get is you don't get carboxylic acid. What you get is a salt of the carboxylic acid. So the carboxylic acid will eventually react with the alkali to give you a salt. So the ester link over here is going to break and it will hydrolyze. Is this clear?
Yes, sir.
Now, the enema spectrum of butanben in CDCl3 contains one or more peaks that shows a triplet splitting pattern. State the number of peaks in the spectrum that show a triplet. I think he's talking about this one. So triplet splitting pattern. So what is the splitting pattern rule? That if your neighbor has n hydrogen atoms, then it's an n+1. It's going to be an n+1 split. That's the rule for. So that's your rule for splitting. So you've got you're going to have all these peaks. These hydrogens are exactly the same, so they're going to resonate at the same frequency. These two hydrogens are going to resonate at the same frequency, and these hydrogens would resonate at the same frequency. And then you'll have these N hydrogens, they have the same chemical environment. And then you have these 4 benzene hydrogens over here. So basically you're going to have, as a circle the peaks you identified in C1. So you have to circle those ones. So I'm going to put a tick next to it. This one will exhibit a triplet splitting pattern. Why? Because the neighboring carbon has 2 hydrogens. The neighboring carbon to this one has 2 hydrogens, so it's going to be a triplet peak. This one will be a multiplet because the neighboring carbons are too many, so the interference pattern would be a lot. So you'll have a multiplet peak. This one would also be kind of a multiplet. Both of these would be multiplet peaks. And this one over here would be a triplet. So it's basically this one and this one. If your neighboring carbon atom has 2 hydrogens, it's going to be an n+1 split. Ethan, Mohammed, is this clear?
Yeah. Sir.
Yes. Do you have a question?
No, sir.
I said, describe and explain how the proton enema spectrum in D2O would differ from the proton enema spectrum in CDCl3. Now, CDCl3 is kind of an inert solvent. Now, D2O has D+1 ions because D2O would split like water. It's H2O. So there's a base over here, this base over here. These 2 hydrogens kind of get replaced by D+1 ions. So one peak would disappear. That's what you're going to write. This peak disappears. Remember that OH and NH2 peaks, they disappear when you add D2O. because their hydrogens get replaced by the deuterium ion. And deuterium doesn't resonate because deuterium has 2 nucleons, which is why it doesn't have a magnetic field, and it doesn't. And it's not going to resonate. So remember this, whenever you have D2O, D2O is specifically added so that you're able to identify which one is OH and which one is NH2, because these peaks are going to disappear as soon as you add D2O. And this is the mass spectrum of butyrate peaks. He says that include peaks at 92 and 57. Identify the fragments. So you just have to identify, when you do mass spectroscopy, the molecule breaks down into tinier pieces. So you just have to identify which one would be 92 and which one would be 57. So you can start from there. This is 15, this is 14, that's 29. 29 plus another 14 would give you what, 43. 43 plus another 14 would give you 57. So this entire fragment is going to be 57. So it will be CH3, CH2, another CH2, another CH2. And don't forget to write positive ion next to it. And similarly, I think the other one would be 92, or you can just keep on guessing like which fragment is 92. You can, in the similar way, you can figure out what is 92. Okay, that sums up this last question.
Sir.
Yes.
For the question where you have to circle the protons, which one do you circle?
The triplet ones, these ones, the ones that I've ticked.
Oh, so you just, oh.
I mean, because he said who was giving you a triplet peak. The rule is that if the neighbor has n hydrogens, n protons, then it will split into n plus 1 peaks.
Yeah.
So for a triplet pattern, the neighbor should have 2 hydrogens. So this one would be a triplet. This one, the neighbor is 2 hydrogens. I mean, this one, you've got too many hydrogens. You've got 3 over here, 2 over here, so that's 5. This one, you've got 2 over here, 2 over here, so that's 4. So you need 2 hydrogens in the neighborhood. So this one is a triplet, this one is a triplet. Is this clear?
Yep. All right. Thank you.
So let's move to the previous question, which I think is, so it's about proteins. Proteins are natural polymers. When one particular protein is partially hydrolyzed, the product mixture includes a tripeptide E. Describe the conditions that could be used to hydrolyze E to produce a mixture of 3 amino acids. Hydrolysis, boil with dilute acid. Let's boil it with dilute HCl. The amide links would all break. I think that's an amide link. If that's an amide links. So the amide links will start to break. So that's what's going to happen. And draw the structure of the 3 amino acids produced. So we're gonna draw this. This is one of them. So you've got, remember, amino acid has, you've got 1 carbon atom. That's carbon atom. And there's NH2 next to it. You got carboxylic acid group on the other side. H on top, and there's a carbon chain at the bottom. That's CH. Then there's CH3. And over here, there's going to be CH2. And then CH3. So focus on this carbon atom. That's where your amino acid starts. You got an NH2, a carboxylic acid on one side, and this carbon chain, R group on this side. The middle one over here, what is, it's going to split over here. So again, this is the carbon atom, and this carbon atom has NH2 on one side, right side. It's got C double bond O, which is going to turn into a carboxylic acid if you break it down. It's going to have an H and an R group. The R group in this case is this one. So it's CH2 followed by OH. And then you have the last amino acid. That's your carbon atom with, it's going to have NH2 On this side, it's going to have carboxylic acid. There's going to be an H, and there's going to be what? CH2, CH2, two CH2s. So it's going to have CH2, CH2, and then finally you'll have a COOH. So those are your 3 amino acids that will be produced. Now, if a pure sample of E obtained from aqueous solution, several different types of intermolecular forces are possible between pairs of E molecules. Name the different types of intermolecular forces that exist between pairs of E molecules, stating the groups on the molecules where the forces are acting. So what is E? E is this thing. So he's saying different types of intermolecular forces. Intermolecular forces are possible. One of them is van der Waals forces, like you have this carbon chain. So the carbon chain can have van der Waals forces. So he's saying the type of, so one of them is van der Waals forces. So pair of groups responsible. So that's going to be the carbon chain. I mean, we can open the market scheme how this is answered, but let's say the alkyl chains will have that. Then you can say that the OH groups and the NH, they can form hydrogen bonds. So there's going to be hydrogen bonding. As you've got OH groups, you've got NH2 groups. So these groups would be responsible for hydrogen bonding. Let me just. So how is he answering the pair? Achha, so, I mean, this is allowed. London forces is van der Waals forces. I'm not sure why they're using London forces, but this is van der Waals forces. So it was between alkyl groups. So we answered that properly. This one also hydrogen bonds, NH and OH. And anyway, so the last one that you're going to have, you got plenty of options. The last one is that the C bond O is polar. So it's going to have permanent dipoles as well. So that would be the last type of intermolecular force. Remember we did primary, secondary, and tertiary structures. So permanent dipoles, C bond O groups would be responsible for permanent dipoles. And there could be ionic bonds as well. You could have, I mean, you've got carboxylic acid, you've got NH2, so they can accept an H plus 1 ion and they can lose an H plus 1 ion. So that's where an ionic bond could also be formed between 2 tripeptide molecules. Is this clear?
Yes.
Now you've got a question on transition metals. So explain what is meant by a transition metal. The definition is that it's an element that is that will form stable ions with incomplete d subshell. So any metal ion that's capable of forming stable ions with an incomplete d subshell is a transition metal. Not all the elements in the boxes are transition metals. Like, I mean, for example, copper is 29. The stable ion of copper is 2 plus. So its electronic configuration is 1s2, 2s2, and so on. You keep writing that. You get 3d10 and 4s2, 4s1. When it's 2 plus, the formula is going to be the 4s, and there's going to be 9 electrons left. So the 3d must be incomplete when it forms an ion, which is why zinc is not a transition metal. Like if you write the electronic configuration of zinc with 30 electrons, what you're going to get is at the end, it's going to be 3d10 and 4s2. The 2 electrons from 4s are lost. And you can see that the 3d is still full. So that is not a transition metal. And the number one thing is it's not going to show colored compounds. Then he says, describe the color changes seen when an excess of SN2 plus is added separately to dilute MnO4 minus 1 and dilute acidified Cr2. Both these he's saying will oxidize. So you just need to know what the color changes are. He's already said that there's going to be a reaction. So KMnO4 changes from purple to, over here, he's saying these oxidizing agents will oxidize SN2 plus to SN4 plus. And he's already said that SN4 plus ions are colorless. So the color is because of the MnO4 magnet ions, purple to colorless. And the other one would be orange to green. And write an equation for the reaction of SN2 plus with Cr2O7 2 minus. So how would you write that equation? You're going to open the data booklet. He said SN4 plus and SN2 plus. That's one reaction. The other one is Cr2O7. So you're going to open the data booklet to the electrochemistry table. And the Cr2O7 equation is this one, 14H plus 1 plus 6 electrons. 2 minus plus 14H plus 1. Plus 7H2O. So plus 7H2O, and this is 1.33 volts. And the SN equation is what? The SN4 plus 1 is this one, it's 0.15 volts. So that one is 0.15 volts. So the rule in electrochemistry is that the higher potential gains electrons. So it's going to go in the forward direction, and the lower potential loses electrons. All you have to do is you have to make the number of electrons gained and lost equal. So multiply this by 3, so that becomes 6. And you add up the reactants. So your reactants are going to be what? 3 SN2 plus. The other reactant is Cr2O7 2 minus. Plus 14H plus 1, and the product is 3SN4 plus 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 7H2O. And that's going to be your equation. You just add up the reactants, add up the products. So this is part of electrochemistry, and it was only for 1 mark. Now, the other one is there's Ru, which forms complex ions, and one such complex ion, the Ru ion, has a coordination number of 6, which means it forms 6 coordinate bonds. Each complex contains Ru2 plus ions, 1 Cl ions, 1 SO2 molecule, and the remaining ligands are NH3 molecules. State what is meant by the coordination number of 6, that it forms 6 dative covalent bonds or coordinate bonds. State the formula of X, including its charge. So you had Ru2 plus, and he said that it had 1 Cl ion, 1 SO2 molecule, and the rest, so there were 4 NH3s. Remember, the 6 coordination number was 6. So this was the complex ion. That the Ru2 plus ion was surrounded by 6. It was making 6 dative bonds. It was surrounded by Cl minus 1, SO2, and 4 NH3s. So it's going to be, what will be the overall charge? It's going to be 2 plus minus 1. So it's going to be plus 1 because the other molecules are neutral. And you're being asked to draw the 2 isomeric forms of this thing. So remember, it will be surrounded by 6. So it will be surrounded by 6 dative bonds. So remember to draw the 3 axes. So the 3 axis, that's, and then there's going to be your Z axis. So here are your 3 axes. So one of them would be that the NH3s are, remember RU is 2 plus in the middle. So the NH3 lone pairs are getting attracted to the RU 2 plus ion. And all the NH3s are lying in the same plane. And the Cl minus 1 is sitting at the top. And the SO2 molecule also has a lone pair on sulfur. It also has a lone pair on oxygen. So that's how it's going to look like. And you'll put a square bracket around it. And overall, it's going to have a charge of +1. You don't write the individual charges because now once the bonding has happened, you're going to have an overall charge. So is this clear? Ethan, Mohammed, is this clear?
Yes, sir.
Now, the other one would be that over here, the Cl and the SO2 are opposite to each other, making a 90-degree angle. So you're going to have another isomer of this. And the only difference is that they would be next to each other in the next one. So same type of bonding. You get that bond is coming out of the page. And now you're going to have the Cl -1 with its lone pairs and the SO2 with sulfur's lone pairs, they would be next to each other. And the NH3s will not be in the same plane. Like there's going to be, there'll be one on top, one at the bottom, 2 of them on the sides. So they're no longer in the same plane. So that's going to be your other isomer. One of them is cis, the other one is trans. So so you had to show how each ligand was attached, everything. So we did show this. TK. I'll check with the, we drew the 3-dimensional shapes. So this one. You can clearly see over here that the only difference is, I mean, they drew different axes, but it's exactly the same. Like over here, the Cl and the SO2 are opposite to each other. And over here, the Cl and SO2 are next to each other, 90 degrees to each other. So you could have shown different axes. So it's kind of the same thing. I just suggest the type of isomerism that's geometric. Because in one of them, they are opposite to each other. In the other one, they're next to each other. Explain the origin of the color in transition metals, such as X. So I think he's talking about this one. So why do transition metals have colors? The reason transition metals have colors is because they've got a D subshell. Like D subshell is this thing. See, so they have a D subshell, which is this one. Now, if you look at a D subshell, the electron density, the negative charge of the electron lies in 5 different orientations in 4 lobes. So it could be in the YZ plane, it could be in the XZ plane, it could be lying in the XY plane, it could be on the X and Y axis, or it could be on the Z axis. So the electron could, now if you look carefully, 2 of them, the electron density lies on the axis, the negative charge lies on the axis. In these 3 orientations, the negative charge lies between the axes. So if I draw all these D subshells, remember D subshells are not the ones that are involved. D subshells are, like we did the electronic configuration somewhere. So the ligands are attached on the outside. The d subshell is inside the atom. It's in the inner shell. You can remember the transition, the ligands are getting attached, the lone pairs are getting attached on the outside of the ion. And the d subshell is in the third shell, it's inside the atom. And the d subshell has to be incomplete. Now what happens is, why do they have colors? The reason they have colors is because once ligands come in, and once these ligands come in and they start sticking on the outside of the atom. So let's draw the outside of the atom. So let's say this is the outside boundary of the atom. So these ligands, they come in and the lone pairs, they start getting attracted to the Ru ion. And the ligands kind of come and stick to the Ru ion. Now you've got these d subshells which are inside. Now these d subshells, some of them are between the axes. So the electron density lies between the axes. And some of the d subshells, their electron density lies on the axis. So in some of them, the electron density lies on the axis. So let's say these brown ones. So I've drawn all the d subshells which are inside the atom. So the d subshell which we saw over here, there are two types. One of them, the electron density lying between the axes. One of them, the electron density lying on the axis. So I kind of drew a rough sketch of how the d subshell would look like around the nucleus. Electron density between the axis, electron density on the axis. And once an octahedral complex is formed, then it kind of becomes really difficult to keep electrons on the axis. Why? Because all the lone pairs are coming on the axis. So it becomes kind of difficult to keep electrons. Now, previously, the d subshells were all identical. They were degenerate, which meant they had the same energy level. The only difference was their orientation was different. They were all exactly the same. But once a complex is formed, it kind of becomes harder to keep electrons on the axis because you got a lone pair on the axis, which is outside, but still there is a fair bit of repulsion. It becomes easier to keep electrons in the middle of the axis. So this is the first thing that you're going to write, which is that explain the origin of the color. So you're going to say that due to lone pair repulsion from ligands, so due to these lone pair repulsion that you see over here, the lone pairs repelling the electrons in the inner d subshell. So due to lone pair repulsion from ligands, the d subshell splits into two energy levels. It splits into two energy levels. So previously you had all these orbitals exactly identical. But now the middle spaces, the between the axis spaces, it's easier to keep electrons. So there's an energy gap that's created between them. There's a space where it's harder to keep electrons, which is on the axis. More difficult to keep electrons. Between the axes, easier to keep electrons. So easier to keep electrons in the green D subshell and difficult to keep electrons in subshells that lie on the axis. Is this clear? Ethan Swear, is this clear?
Yes, sir.
So what happens, it splits into two energy levels, and the next thing you're going to write is that electron from the lower energy D subshell gains energy by absorbing a frequency from the visible spectrum. So it absorbs a frequency from the visible spectrum, and you're going to write that E is equal to HF as the energy gap. The energy gap matches and a complementary color is seen. And moves to the higher energy D subshell. And a complementary, so it's going to, if the ion absorbs red, you're not going to see red. You're going to see all the other colors. So, and a complementary color is seen. So whatever he absorbs, you're not going to see that. You're going to see the opposite. So the complementary color is reflected or seen. So that's the answer to this one. Okay, so it's which one? So you're going to write about just the 3 marks for this. Electron promoted, so we gave that idea. Complexes splitting into d orbitals of 2 different energy levels. We did that. Visible light getting absorbed, so we said that as well. So due to lone pair repulsion from ligands, d subshell splits into 2 energy levels. Electron from the lower energy d subshell gains energy by absorbing a frequency from the visible spectrum. So that's also done. And moves to the higher d subshell. That's the promotion that's happening. Is this clear?
Yes, sir.
You can remember this is a standard answer for whenever you get a color, you have to just remember this answer. Another thing is another thing about the same question is they might also ask you about why does the color change when you change the ligand? Because you're going to have a different lone pair repulsion and a different energy gap is going to be created between them. If a different energy gap is created, a different frequency from the visible spectrum would be absorbed. So they're going to ask you about that. Why do different complexes have different colors? Because they've got different ligands as well. And there's a different repulsion. So a different energy gap between the two. It's going to have the same splitting, but it's going to be a different energy gap. So is this clear?
Yes, sir.
Yep.
Now explain the variation of the solubility of group 2 metal sulfates. Sulfates, they decrease down the group. And again, this is a very typical standard answer. Solubility decreases down the group. Now remember, when you have to dissolve a substance, you have to do 2 things. You have to make it aqueous. That's the overall thing that you have to do. You just adjust an SO4 -2. So that's your enthalpy change of solution. Now the cycle is you would have to break the lattice first. You have to split up the ions. The ionic lattice needs to break. That's negative of lattice energy. That's an endothermic process. And then the ions need to dissolve in water and bond with water and form complexes. So that's hydration, which is exothermic. So overall, when your solubility decreases down the group, that means overall the enthalpy change of solution is becoming more and more endothermic. So as delta H solution becomes endo down the group. Now, why does it become endo? Because cationic radius increases down the group. it increases down the group. Now, when it increases down the group, cationic radius increases down the group. What happens is that that both lattice energy and the hydration, they form weaker bonds. So both of these values would decrease, lattice energy and delta H hydration. Decrease. But since the solution is becoming more and more endothermic, so the lattice energy is relatively larger compared to the enthalpy of hydration. So it's becoming more and more endothermic down the group. So down the group, lattice energy.
Sir, is lattice energy endothermic?
Which one?
You said negative. Oh, is it because negative lattice
Yeah.
energy? That's what it's
Yeah, because
endo.
yeah, because by definition, this is the negative of lattice energy. You're breaking the lattice, right? I mean, lattice energy is exothermic, but over here, we're not forming the lattice. It's the negative of lattice energy. You're actually breaking the lattice. So down the group, lattice energy is going to be relatively bigger compared to delta H hydration. Hence, it's going to be more endothermic. Is this clear?
Yes, sir.
And when it comes to hydroxides, the enthalpy, they become more soluble. So that means enthalpy of solution is becoming more exothermic. And if it's becoming more exothermic, that means that both of these would decrease. But relatively speaking, down the group, hydration would be bigger compared to lattice energy. The exothermic term would be bigger compared to. Now, this one, elements in group 2 include magnesium, calcium, strontium, and barium. Write an equation for the change representing the first. So what I'll do is, I mean, you can pretty much do, we'll try and see more NMR questions, just a second. The last ones. So just let me. So maybe let's see what happened here. This is summer of 21. So this one, so I've never actually attempted this question. So let's try this one. Now you're saying that carbon-13 NMR spectrum of compound, this thing, C8H8O2, contains 6 peaks. So that means although you've got 8 carbons, but there are 6 carbon environments. Now, one hunch that I can have is whenever you have a ratio of carbon to hydrogen that low, that means it's a benzene. So it's C8H8O2. So that is, I mean, definitely has a benzene. So I'm just going to draw the benzene over here. So 6. So you've got a benzene, C8H8 and O2. So what about the other 2 carbon atoms? So remember 6 environments. We'll just wait for the other information to come in. But remember 6 environments. I mean, at the moment, I mean, it can't be just a benzene because then it's going to be just exactly one environment. All of them are identical. They have exactly the same environment. If I even attach any group to it, then that would indicate that this carbon has a different environment than the rest. These 2 carbons are identical. These 2 carbons are identical. And this carbon has a different environment. Now, but forget this at the moment. We don't have enough information at the moment, but I do know that it's a benzene. And it's got to have 6 It's got to have 6 carbon environments. As it reacts with an excess of bromine water to give this thing. So it reacts with an excess of bromine water. So who reacts with bromine? It's either a phenol. Remember, phenol is activated. So it's either a phenol or something that has a double bond, like the remaining 2 carbon atoms. They might have a double bond. Not really sure. Then he says that it reacts with alkaline to form a yellow precipitate and compound D. So yellow precipitate is getting formed. So the yellow precipitate alkaline aqueous iodine, that's iodoform test. You get an iodoform test for 2 things. It's either CH3CHOH or it's CH3 C double bond O. Anyways, that kind of does our job for us because we figured out what were the 2 remaining carbon atoms. We knew that the 6 carbon atoms were benzene. So out of the 8, I'm now pretty sure what are the 2 other carbon atoms doing. They're either this one or this one, right? So because the iodoform test is positive. So it's either going to be CH3, CHOH. Ethan, is this clear? Mohammed, is this clear?
Yeah.
Yes, sir.
Or it's going to be the other one, which is C double bond O. So what are you left with? You're left with so it can't be, I mean, we figured this out. So it can't be this alkene thing because the 2 carbon atoms are busy doing the iodoform test. So it must be either one of them. So it has to be a phenol. The other thing is it must be a phenol. So I'm going to add an OH group to it. I'm going to turn this into a phenol. So I'm going to add an OH group to both of them. And we can then easily reject. So after that, we can kind of easily reject. Just count the hydrogens, C8H8O2. So who's got 8 hydrogens? I think it's going to be, who's got 8 hydrogens? That's 1, 2, 3, 4, 5. So this is the molecule. This one is not the molecule because this is C8, H8O2. Now, the other thing is, I don't know what the position is exactly. I'm not sure what the position is. Is this clear? I mean, that's the only thing. We can do the other test now. He's saying it reacts with PCl5 to form compound E. So, and the compound E is this thing. It reacts with PCl5 to, actually, sorry, he's talking about D. And E reacts with to form compound F. So let's focus on this one. 6 carbon environments. We need 6 carbon environments. So that's 1. These 2 are identical. They're exactly identical. So that's your second carbon environment because remember the chemical environment around them is exactly the same. This one is the third one. I mean, these 2 carbons are exactly the same, bonding wise. Then this carbon is separate, different from all the other ones. That's the 4th one. This one is the 5th one. And this is the 6th environment. So we got our 6 environments as well. Is this clear?
Yeah.
So does
yes.
the C have to be bonded to a H?
For the NMR?
Yeah.
Remember, this is carbon NMR. There are 2 types of NMR. There's an H NMR, and then there's a carbon 13 NMR. This one is carbon 13 NMR. I think this is the carbon 13 NMR. Carbon 13 NMR, you basically look at the carbon environment. So the carbon starts to resonate because carbon has an isotope, which is 13, and that resonates because it's got a net.
So the splitting pattern and all the same?
everything is the same except that carbon-13 NMR, they don't have a splitting pattern. I mean, carbon-13 NMR is exactly the same as HNMR. Whatever you do for H, you do the same thing for carbon. The only difference is it's not going to have a splitting pattern. They're always singlet peaks, that's it.
Okay, so, all right.
In HNMR, you got a splitting pattern that if the neighboring H has 2 hydrogens, it splits into 3. If the neighboring carbon has 1 H, it splits into 2. So there's an n+1 rule there. That's not going to be here in carbon-13. Carbon-13 would all be singlet. Like if you look at any carbon-13 NMR, it's only going to be, I mean, look over here, it's all singlets, that's it. So, I mean, look at this molecule, like over here. This carbon is different from all the others. Then you've got this carbon that's being different from all the others. I mean, these 2 carbons are different from each other. So how many environments? You got 1, you got 2, 3, 4, 5. So there are 5 different environments. So that's 1, 2, 3, 4, and 5. So there are 5 different environments in this case. We can check this one out as well. And the values are given in the data booklet, like not this. So let's just to think that carbon-13 NMR is kind of simpler.
So there's no M+1 peaks, right?
Hey, that's mass spectroscopy.
Oh, okay.
Tika, that's something different. That one is mass spectroscopy. So which paper were we doing? This one? This one. So remember, whenever you have a carbon, it's going to be very simple. For example, you've got this molecule. So how many different types of carbon do you have?
2.
2. I mean, there's this carbon that's different, and these 2 carbons are exactly the same. So the spectrum would be just 2 peaks. One would be for the CH3, one would be for the serial bond O. That's it. The tricky part is benzene, the benzene part. Always remember, like this one. Look at the benzene. I mean, you've got this carbon that's different from the others. You got this carbon that's different from the others. Remember, these 2 carbons are exactly the same. I mean, the environment is exactly the same. They're bonded in exactly the same way. And these 2 carbons are different from these 2 carbons because these 2 carbons are bonded to this CHOH and these 2 carbons are bonded to this other carbon. Is this clear?
Yes, yes, understood.
So it's going to be 1 environment, 2nd, 3rd, 4th, and 5th. But what if you had a benzene or any cyclic structure? And this time it was like this. There was CH3 and the OH was over here. Now look at the carbons. The carbons, I think all of them would be different. You got this carbon, you got this carbon. Now these 2 carbons are not in the same environment. Is this clear? Because this carbon has an OH right next door. So this carbon is different from all the others. This carbon is different from all the others. This carbon is different. All of them are going to be different. Is this clear?
Yes, sir.
But over here, because of symmetry, these 2, the one on top and the bottom, they were exactly the same.
So how would you draw the peaks? So like the peaks.
It's just you just have 1, 2, 3, 4, 5, 6, 7. You just have 7 different peaks according to whatever the environment is. Like where's the data booklet? So here's your data booklet. And there's a table for carbon 13. And I think okay, here's my table for carbon 13, just a second. This one. This one is the carbon 13 chemical shift values. So if there's an alkyl carbon, that's 0 to 50. If there's a alkyl carbon with a double bond or with next to a benzene, that's 10 to 40. So most of the stuff, I mean, you can identify the carboxylic acid or the aldehyde, like the C double bond O, carboxyl or carbonyl. Carbon, that's 160, 220. You can kind of identify that one easily. The benzene carbons can be identified. They're unique, kind of unique. So the values are given over here. Is this clear?
Sir.
So we're able to figure out the molecule. All you have to do now is draw the, I mean, what was the molecule that we figured out? This one, right? So all you have to do now is draw what's going to happen. So you got a benzene with, I think, methyl ketone. That's what we figured out. And it had an OH. And these were hydrogens. So it's going to split up over here when you add alkaline aqueous iodine. So you'll have benzene. This C double bond O will turn into carboxylic acid, and you got an OH. And the other one is this will turn into CHI3. That's the yellow precipitate that's going to be formed. Actually, I've written it wrong. This one is the yellow. I mean, this is the yellow precipitate. And the conditions are alkaline. So if the conditions are alkaline, it's going to form a salt of the carboxylic acid. And remember, phenols are also acidic, so it will also form a salt. So this is what's going to be formed over here. And then I think, did he give us the formula of the molecule? No, he didn't actually. And then he says that D reacts with PCl5. What's going to happen when D reacts with PCl5? Did he acidify it? No, he didn't. Let me just check the marking scheme as well. It's definitely going to.
Acylation.
It's going to be acylation. No, not acylation. The PCl5 is used to remove the OH. So just 1 second. So I think this was the last question. This was the molecule, right? We did. So yeah, it is acylation, but CHI3, why did he not make it a salt? Because the conditions are alkaline. This is something that he should have done. So that's the issue. Did he say that he acidified it? Like he's adding alkaline aqueous iodine, and he's adding alkaline aqueous iodine. So in an alkali, it should not form a carboxylic acid. It should form a salt. But anyways, the carboxylic acid OH is going to get replaced by. I said, remember you said acylation. Acylation is a separate reaction. In acylation, what happens is an acyl chloride, its carbon positive gets attracted to a benzene. That's acylation. Over here, an acyl chloride would be formed. Like the benzene, the carboxylic acid will lose its OH, and it will form Cl. Is this clear?
Yes, sir.
Acylation is this thing. Over here, acyl chlorides are getting formed. And then it reacts with propan-2-ol. So it's going to form an ester. Propan-2-ol, it's going to form an ester. The Cl and the H are going to be lost. and this carbon with bond with an O, so they would end up forming an ester over here. So this is what's going to be formed. And sorry, it's propane 2 all. So the OH must be on the middle carbon atom. Okay, make sure you do that correction. And he reacted with bromine, so it's an activated benzene. So bromine would get attached to position number 2 and 6 on these two positions. Like I can draw it over here. This is where the bromines are going to get added to. So where's the bromine? It's going to be attached to the second and the fourth. Due to the OH, what happens when you have an OH? The lone pairs, the electron density increases on this side. So the bromines get attached on this side. Is this clear?
Yes, sir.
So then you have this so it's a moles question, I think, that was dealing with. So the question is the sketch graph for ethanoic acid with sodium hydroxide. So the point is, you see in the region circle on the graph, identify 2 organic species that are present. So I think he's got ethanoic acid at the bottom, and he's adding sodium hydroxide from the top. So in this region, equivalence or neutralization has not happened yet. So that means some of the ethanoic acid would have been neutralized to form the salt, and some of it would still be unreacted. So he's saying 2 species present, 2 organic species. So some of the ethanoic acid would still be present, and some of it would have turned into its salt because it would have reacted with the NOH that's coming from the top. Is this clear?
Yes, sir.
And why does the mixture pH changes slowly? Because it's a buffer solution. Because you've got a weak acid and you got its conjugate base as well now. So you're going to write your 2 equations like if you, so you say explain the pH gradually when NaOH is added. So when NaOH is added, what will happen is the OH ions will get neutralized by the ethanoic acid. And it would turn into CH3CO -1, and water would be formed. So that is what happens when OH ions are added in a buffer solution. When an OH ions are added, the weak acid starts acting as the weak acid. It starts neutralizing it. And when the H+1 are added, vice versa, the conjugate base is the one that starts accepting those H+1 ions and neutralizes them as well. So in this case, you've got you're going to write this equation. Okay, that's going to be the answer to this. That it's got both. So a buffer solution is formed, and you can write this equation, which is that ethanoic acid reacts with the OH ions. We wrote that equation. That's mark number 3 for that. So forming CH3CO2 -1 and water. So that's exactly what we wrote over here. And then he says, why is the equivalence point pH greater than 7? Why is it 7? Once equivalence has happened, equivalence is the point when all the ethanoic acid has reacted with NaOH. Equal moles have been added. So what will happen is that CO -1 would be formed and water would be formed. So you got these 2 things in the solution. So the question is, if these 2 are formed, salt and water are formed, why is the pH greater than 7 at equivalence? And the reason is, this is a strong conjugate base. Remember, it's a base of a weak acid. Whenever a weak acid forms a conjugate base, the conjugate base is always strong. Is that clear?
Yeah. Yes.
So what it will do is, basically what that means is that the weak acid doesn't want to ionize. It doesn't want to form this ion. So it will react with water and pull some of the H+1 back, because the ethanoic acid did not want to get ionized in the first place. So it will form OH ions. That's why the pH is more basic, even though equivalence has been reached, because ethanoate ions don't like to form ethanoate ions. They want to remain as ethanoic acid. So they're strong conjugate bases, and they're going to try and pull those H+1 back again. So they're going to split the water into OH ions and pull those H+1 back, some of them, which is why at equivalence you don't have a neutral pH, you instead have a basic pH. So Riga, let's try the weekend classes, TK. We'll try and do more questions. Try and complete this paper. See if you have any problems with this. This one is summer of 21, question paper 4.1. TK.
Yes, sir, could you also discuss partition coefficients?
Partition coefficient is my pen, just a second. Partition coefficient is when you have two immiscible liquids, like any two, oil and water. Doesn't really matter what those liquids are. You add a certain substance X, then a certain amount will dissolve in oil and a certain amount will dissolve in water. And there's going to be an equilibrium, which is that the substance would be moving past this partition. So this certain substance X would be in oil and it would also be in water, and there's going to be an equilibrium. It would be passing through the two layers. If it's more soluble in water, then there would be more of it in water and there's going to be less of it in oil. But there's still going to be an equilibrium over here. Whenever you have an equilibrium, that's partition coefficient. That is the product over reactant ratio of the partition, which is, it would be the concentration of X in water divided by the concentration of X in oil. It's usually calculated in gram per cm cube because there's no point in calculating the the moles, because the MR is the same for both. So it's going to get cancelled out. So you just use gram per cm cube and you get the partition coefficient. If the partition coefficient has a large value, that means there's more of X in water than oil. In this particular case, if the partition coefficient is coming out to be a smaller value, that means there's more of it in oil compared to water. It's more soluble in oil compared to water. Is this clear?
Yes.
So that's about it. So we'll try, in the next class, we'll try and do some questions on partition coefficient. Okay? So there are two types of questions. One is where you have to calculate partition coefficient. The other one is that the partition coefficient would be given and you have to do the reverse. Okay, so we'll try and do those questions. Let's try the next class then. Okay.
Yes, sir.
Okay.
Thank you.
Thank you, sir.
Okay, take care.